welcome everybody again. And I would like to introduce our today's speaker, Wolfgang, who is lead engineer and consultant in Luxoft. He's based in Germany, and today we'll talk about validation of driver monitoring systems. So, Wolfgang, I'm passing the floor to you, please.
Yeah, thank you, Julia, for this nice introduction and having me here at the Automotive Marathon. I will talk about validation on driver monitoring systems today. And before we start, I would like to explain you here all the logos you see on the first page of different companies. Luxoft and now also CMORE belong to the DXC technology family, and since this year CMORE Automotive, where I am working at, is a 100% daughter of Luxoft. I wanted to mention it here because maybe you find some other presentations on this topic with templates of our old company CMORE. This is still the same work, but now in a much bigger company. So we are very happy to being here, having the opportunity to talk to so many people in this talk, and I think we should start immediately. Well, the agenda for the next 30 to 40 minutes is first a short overview on driver monitoring systems for mass production cars. I will explain a paradoxon, namely that driver monitoring is an enabler for autonomous driving, and then we'll give you an overview of all applications that are known in mass production cars which use driver monitoring systems in these days. With this, we will see which driver monitoring system or DMS signals are calculated by a driver camera. This is the basis for the validation part in the second part of the talk. And then at the end of the overview, I would like to give you a short overview of the legal requirements in the European Union and of Euro NCAP. Then in the bigger part of this talk, I will give you an overview of the online ground truth systems we developed at CMORE Automotive. On the one hand side, to avoid as many manual labeling as possible, but you will see that there are still topics where labeling is necessary. So there will be a very short part on labeling. And I think only one slide about special requirements on data collection. I think this is important to know. If you think of advanced driver assistance systems, you usually think of one professional driver driving around for thousands of kilometers. Here it's the way vice versa. You need hundreds of drivers, and the environment outside is not that interesting. Okay, let's start with driver monitoring systems for mass production vehicles. And as I announced with the paradoxon that driver monitoring is an enabler for autonomous driving. I'm completely convinced that at least for the next 10 years, it can be assumed that a driver will still be needed to take over control in situations where a car that is more or less driving autonomously is necessary, because if you imagine that we have one bad accident every 10 million kilometers, and if you drive with an average speed of 100 kilometers an hour, then you have one bad accident within 100,000 hours. And developing systems that can deal with probabilities of 1 out of 100,000 hours is very complicated. And this is why we often think that we already have cars that are driving autonomously. They are driving themselves, but they cannot take over the responsibility for all seldom and strange situations. And with this, you need a driver who is able to take over responsibility in situations the system cannot deal with. We call this conditionally automated driving or level 3 automatization. And to ensure that the driver is not sleeping or completely out of the loop, we need a driver observation that ensures that the driver can take over the responsibility. And this must be done with driver monitoring systems, because driver behavior cannot be observed, because the driver is driving hands-free and the car is driving itself. So we need a driver camera. So this was an enabler for mass production cars 5 to 10 years ago. But up to now, we have a lot of other interesting applications that can be seen for mass production cars in driver assistance systems and passive safety. We talk about drowsiness detection and automated driving, as said before, but also multi-level airbag deployment depending on the size of the driver and the known exact position of the driver's head are under development at the moment. But also in the area of user interaction, topics like driver identification, similar to identification with your smartphone, can be done with a driver camera. Autostereoscopic displays that are now introduced with the new Mercedes S-Class need driver observation, and contact analog augmentation in head-up displays, as you can see here. Also, the first pictures of the brand new S-Class, when you want to augment a red line here on the street, you have to know the driver's head position, because if you move your head to the left and to the right, then this line will also start to move a little bit, and here you have to compensate this movement with the knowledge of the driver's head. Other interesting topics that are a little far away from mass production, but also very, very interesting, are facial expressions for the detection of emotions. You can measure heart rates to look for the driver's healthy. Although this is still a little bit problematic due to vibrations in mass production vehicles. With all these applications, you come up with the following signals. You need the so-called head pose that consists of a position and a direction. So we talk about a 6D head pose of the driver, XYZ for the head position, and yaw, pitch, and roll angle of the orientation of the driver's head. Then topics like gaze control or eyes on road detection need the driver's gaze. For drowsiness detection, for instance, eyelid closure values are needed, so you need the degree of the eyelid closure or the eye opening, depends on how you define it. For driver identification, you must detect known and unknown drivers, and for facial expressions, you have to test neutral faces, laughing, sad or angry, or other faces to see whether facial expressions can be recognized. One very important point for driver monitoring is what happened in the European Parliament and in the European New Car Assessment Program, so Euro NCAP, in the last years. Since more than 5 years, it is discussed that driver drowsiness and attention warning and distraction warning shall be implemented as a must in the European market. And if you look to the legislative resolution of April 2019, it is said that the date for the prohibition of the registration of vehicles, as well as the placing on the market and entry technology units, was expected to be done in 2022. The latest information is that due to the corona epidemic, this is delayed to 2023. But after 2023, new cars need driver observation systems. And if you want to drive at least level 2 with these cars, it's mandatory to have driver monitoring systems. This is similar to, or the next step is an advanced driver distraction warning. In 2002, in Germany, could have seen a lot of big pictures on the highway showing this guy and in big letters the question, and who is driving. And what we expect for 2022-24 is that driver monitoring systems are able to detect all this. So it's necessary that a system detects whether a driver is smoking, whether a driver is doing a phone call, whether he is eating or drinking, or doing other things that distract the driver inside the car. The Euro NCAP also reacted on this and investigates an incentive for a driver monitoring system that effectively detect impaired and distracted driving. Of course, it is assumed that an appropriate warning and effective actions are taken by the car. So with this, we know that driver monitoring is an important topic for the next couple of years. It's not that much known in the area of autonomous driving. Everybody is talking about robocars and cars that drive without any interaction with the driver. But this is what we expect for the next couple of years. At CMORE and now also at Luxoft, we offer a lot of possibilities for driver monitoring system validation, starting with consulting projects for OEMs, tier 1s, tier 2s, the setup of all ground truth systems, or the further development of new ground truth systems, the integration into test cars. This will not be my topic of today. Then data collection, data annotation, so labeling, and of course at the end the KPI analysis. Let's start with the online ground truth systems, and the first of it is our so-called HeadGT. It consists of a motion capturing system, a headband, and 2 calibration targets, as can be seen here in this picture. Andre, you asked a question. I will go through this afterwards because it's not a question of understanding. If you have any questions for understanding, please, Julia, take a look at it and interrupt me. I will answer them directly, but general questions I think we can discuss at the end of the presentation.
Yeah, so, sure. I'm checking.
Great, thank you. So our HeadGT consists out of a motion capturing system. It's a one-box design with a stereo camera that is about 42 centimeters. It is mounted at the top side window of the passenger seat instead of the passenger assist handle. So here we can really have a very robust connection to the body of the car to avoid any vibrations. And if a car has window airbags, they must be deactivated for the tests. The frame rate with the old system is 60 frames per second. We are now able to deal with more than 100, 120 frames per second. But the driver cameras with the biggest frame rate up to now use 50 to 60 frames per second. So this is completely enough for the moment. The head target is a headband that contains IR reflective markers for the motion capturing system. It can be placed on the head of the driver, like a helmet for your bicycle. And on the one hand side, it's very comfortable, and on the other hand side, it does not slip if you move around a lot. And I've worn this for 6 to 8 hours during a test drive. So this is really a good method to use it as a ground truth system. Yeah, as I said, we mounted very robustly to the body of the car, so vibrations are no topic. And this is the overall architecture. On the one hand side, we have a device under test, a driver camera that is usually mounted in front of the driver or somewhere near to the infotainment system. And here we have to receive the data, CAN data, Ethernet data, whatever. But we also need the raw image of the camera. I will explain in a minute why. And our motion capturing system delivers the 6D head pose, namely X, Y, Z, pitch, yaw, and roll angle. And then we have an online visualization, especially for checking that the calibration was good and data recording is obvious. Okay, this is the principle how the head GT is working. On the one hand side, we have the driver camera itself. It measures a head pose with a reference point somewhere in the face of the driver and an origin somewhere in the driver camera. So this green vector is the head pose of the driver camera. And our head GT measures the head pose with the origin of our head target. So it doesn't make sense to compare this vector with this vector if you're interested in accuracies of less than a centimeter. And with this, we need 2 calibration steps. First is our system calibration. Here we use a checkerboard on the one hand side to measure the origin of the driver camera, and this is the only reason why we need raw images of the driver camera. And on the same target, you here have similar IR reflective markers as I have shown you here. Oh, sorry, on the headband, like these. So with these markers, we can measure the origin of our head GT. So with this calibration step, we know this this vector from between the 2 origins very well. The last step that is missing to bring this reference point to the reference point of the driver camera. And if we know how the driver camera calculates its origin, usually this is done by eye corners, and then a mid-eye point is calculated. We use this head calibration target. It has a dip, and the driver is asked to place this dip into the eye corners and to the subnasal or to the mouth corners, depending on how the driver camera is calculating its origin, its reference point. And if we have this, then we also know the coordinate transformation from the head GT target to the driver camera. And then the sum of these three vectors can be used as an exact reference for the head GT. If you are interested in a small video of about 3 minutes how this head GT really works, there's a YouTube video available. You will receive the slides afterwards and can have a look at it if you like. This is the last slide I'd like to show you to the head GT. What we do is let's call it a KPI pre-analysis. It is well known that if you make mistakes in the definition of the coordinate systems, that big head movements in X direction also have influences in the other components. So what we do in the first step is doing some pre-tests where the driver is told first to make head movements forward, backwards, to the left and the right, upwards and downwards, shaking and nodding and rolling the head. And then we have a look at the graphs to see whether this is reasonable. If you do not do this and start directly with statistic analysis, then you might have strange results that only occur due to different definitions. Next topic is our gaze GT. The gaze GT is an add-on to the head GT. It consists of the head GT and additionally of a so-called LED system. We place a lot of different LEDs into the view fields of the driver. And if this LED is blinking, like it is shown in this image, then the driver is asked to observe this LED, and then we can measure without any eye tracking a reference for the driver's gaze. This is a suggestion of where to place LEDs. You can also place them outside to the left and right mirror, wherever, whatever region is interesting, view straight ahead on the street, the infotainment system, the instrument cluster, the mirrors, whatever you want. And this is the principle. The driver is observing the blinking LED, and if the location of the LED is known, and if the position of the driver's pupil is known, then you can calculate the gaze vector, and the position of the pupil is approximated using our head GT. We calculate the gaze vector for the left eye and the right eye independently, because if you have targets that are nearby, these vectors are different. Okay, which accuracies do we reach? First, we calibrate our head GT not to the mid eye point as I told you for the head GT, but to the midpoint of the left and the right eye. Midpoint means it's the mean value of the two eye corners. So this blue point is our approximation of the pupil. And you see in this image the pupil in reality is here, and this is the point we assume the pupil is. So here we make an error, but this error is is much smaller than you might expect at the beginning. This is the worst case. If you look very much to the left or to the right, then the pupil that is looking to the inner part in the direction to your nose makes the biggest error. We have seen in an analysis with 20 to 50 participants that this error is smaller than 10 millimeters. Sounds a lot, but it is not, as you will see. Our HGT has an accuracy of about 5 millimeters. These 5 millimeters are not the accuracy of the motion capturing system itself. It's the overall error, and one important part of the error is if you mark the reference points in your face. Here the driver is doing some errors, and with this we end up with an accuracy of about 5 millimeters. The position of the LEDs it can be measured with accuracies of less than 1 millimeter. And the last information we need to calculate the accuracy is that the distance between the driver's head and the LEDs in all cases is bigger than 50 centimeters. The nearest LED is the LED just in front of the driver on the speedometer, and this for small drivers is still 50 centimeters away in passenger cars. In buses and trucks, this is much more, and the error becomes much smaller. And if you now look to a simple Arco-Standards functionality, sum up all the errors you have here and divide it by the distance of 500 millimeters, then you see that the overall gaze vector is smaller than 2 degrees. 2 degrees sounds a lot, but it is not, because the human eye has an area of sharpest seeing that is about 2 to 5 degrees. So if you watch a target in front of you, you will never act as a human with a higher accuracy than 2 degrees, and it doesn't make sense to measure better accuracies than the behavior of human eyes. Here are some pictures of the LEDs. We can use them during drives on public roads because the LED housing is smaller than 10 millimeters. We have very thin cables that cannot be seen by the driver. The LEDs can be dimmed depending on light conditions, and the supervisor and the driver, they both have the possibility to turn off the LED at any time. So if you are in a situation where the driver has to concentrate on the traffic, we interrupt the measurement, turn off the LEDs so that the driver is not distracted by this test. Here you see a KPI pre-analysis again now for the gaze GT. Usually we start with LEDs. We here placed in a lab setup in our office in Eschborn near to Frankfurt. This is the area of the instrument cluster display. These two are more or less the borders of a head-up display. This is a view straight ahead on the street. This is the area where you usually have your infotainment system, sometimes a little bit lower. Sorry, and this is if you look a little down. This is the right mirror. This is the right truck mirror. Here you have a view to the right side of the street. These two, this is the interior mirror and the left mirror, and if you follow this way in this image and look how in azimuth and elevation angles this can be calculated for the ground truth systems with this red track. It's more or less the same. And here you see a starting point of a device under test we have used here. You can say, okay, maybe you have a systematic error, but it is not, because the endpoints here are at the same place. So what you see here, that for gases downwards, you have a big error. For upwards, it's also a little bit underestimated. And this gives you a very good first impression whether gaze measurement worked, whether all the LEDs were used in the correct order. And if you here have strange behavior, again, it doesn't make sense to go on with any statistics. This is why we first look to the images and to the plots, and then start real KPI analysis with statistics. If you're interested in the eye-opening degree, or in the size of the pupil, or sometimes the OEMs are also interested in measuring the diameter of the iris, it's still necessary to use eye labeling. There are some pre-developments also for online ground truth systems, but the only online ground truth system for eye behavior must be a camera-based system, because if you work with any head-mounted device, then the driver camera itself is disturbed by the ground truth system. This is, of course, not allowed. And if you use other remote cameras, then you can say, okay, then similar algorithms in your ground truth systems are working as in the device under test itself. So here, I think it will take some more years to develop online ground truth systems. At the moment, we still need labeling here. We offer 3 different kinds of labeling, with a low accuracy, the upper and lower point of maximum opening of the upper eyelid, and the lowest point of the lower eyelid are marked, and then the distance is measured. A little higher accuracy can be reached if you first mark the eye corners. Then give the labeler a bounding box that is parallel to the line between the from the left to the right eye corner. And if you want to have the highest accuracy, then we recommend not only to label the eye corners, but also 3 further points on the upper eyelid and 3 further points on the lower eyelid. Then we calculate a spline function to really approximate the border of the upper eyelid. The same with the lower eyelid, and then the maximum distance is only mathematics between these 2 functions. This is what we use. This is what we use in big projects with more than 10 to 100 million images. We have a joint venture partner in India to deal with these big amounts of data. This is the most expensive part of driver monitoring system validation at the moment. And we think a lot of improving online ground truth systems, but as said before, this is not so easy than for head position and gaze detection. Okay, let's talk a little bit about data collection. What you see here is the supervisor on the front seat, because the co-driver seat must be empty, because we need a free view of the motion capturing system that is located somewhere here to the headband of the driver. the supervisor can always see the face of the driver. I think here they are performing the head calibration task, but this is also necessary during test drives to see whether the driver is distracted or not, because we have to guarantee safety on and safe and secure driving on public roads. The special requirements for data collection are that we have a lot of requirements for the test drivers. We need to vary the origin, the gender, the age, the height of the driver. We have special requirements on different appearances of the driver: glasses, caps, beards, masks, makeup, face masks. Special requirements on environmental conditions. Darkness is not that interesting because driver monitoring systems usually use active IR illumination. The most challenging situation is bright sunlight, because the IR light of sunlight is also very, very bright, and here you can have problems of if too much IR light is in the face of the driver, that the camera is no longer able to deal with this. And of course, drop shadows. If you have sunlight from the left, then one part of the face is very dark, the other one is very bright. This is interesting. So we often have to deal with sunlight, but this is more or less all. It's not really important where to drive. Of course, we have to deal with all the online ground truth systems to explain the drivers how to do this. And if you look at all this, you can imagine that that for data collections you need very experienced supervisors, and these supervisors should be in the test car together with the driver. Sometimes you have additional customer-specific requirements on test tracks. What we have at the moment is a test database with more than, you see, 400. I think it's much more than 500 drivers. Because if you want to vary all this test campaign for the validation of a driver monitoring system for mass production cars, needs at least 400 to 500 different drivers. We have to deal with data protection regulations. Of course, it's not possible to anonymize the driver's face. You cannot have a bar in front of the eyes if you're interested in the eye-opening degree. So here we need contracts with each driver to be allowed to use this data. Can imagine we have to manage a large amount of data here. This is similar to all other camera-based systems like multipurpose cameras that observe the car's environment. Okay, I'd like to finish my presentation with a short overview of what we have done in the last 4 years. We started with projects on developing our ground truth systems in 2016, and have had projects with OEMs, tier 1s, tier 2s. We have consulting projects, vehicle integration, data collection, data annotation, missing an I, and KPI analysis since this year. So now we are able to offer an end-to-end validation from consulting to KPI analysis. So thank you very much for your interest, and now I think we have quarter of an hour, 20 minutes for questions. Julia, do you have an overview?
Yeah, actually we have 14 questions, which is really, well, a lot of questions. So, and
Okay.
we have even two questions regarding glasses. I
Mhm.
mean sunglasses. Like, what if the
Yeah.
driver wears sunglasses?
Mhm.
Uh, does it influence the detection?
Yes, it influenced the detection. It depends on how the sunglasses are built. Uh, there are sunglasses that are completely transparent in IR illumination. And then then sunglasses can be an advantage for a driver camera, because if you imagine you have the sunlight coming directly in your eyes, and you're driving like this with a very small eye opening degree, and then you wear sunglasses with completely open eyes, and IR light can look through the sunglasses like through usual glasses, then this is a big advantage. But there are also sunglasses that are completely intransparent for IR illumination. And with this, one important signal the basic signal I haven't talked about here is the detection whether the eyes of the driver are visible or not visible. And if for a long time, because of sunglasses, the eyes are not visible, then the driver should be informed that maybe because of his glasses or for some other reason, all the systems I showed before cannot be activated because the eyes of the driver are not visible.
Okay, next question from Alexey Stolerov. What for emotion recognition is used?
Yeah, there are especially for premium cars, some people in pre-development are interested in offering the driver some special music or some massage on the driver's seat if you based on the emotions of the driver. But this is, as I said before, still a pre-development, but you already have different forms of ambient light, massage seats, and so on. And these guys in automotive industry are interested in motion detection. Some people are also interested in bringing the driver down if he is very angry in a traffic jam on a highway, to tell him, hey, maybe it's a good idea to cool down. But this is, as I said, still a pre-development. Tesla, Eugen asked, yeah, Tesla has a driver monitoring system or a driver camera available in his cars. He wants to use for level 3 in the future. It's placed in the interior mirror of the cars. This, from my experience, is not the best position, because you should have a position of the driver camera that is below the driver's eyes. So if you look into the eyes from downwards, it's much easier to see the eyes. If you have a driver camera above the driver, and if you imagine a European driver who has a border here between the eyes and the upper part of the head, then you can have occlusions of parts of the eye. This is completely different for Asian faces, but especially for European faces, the position Tesla is using at the moment is not optimal.
Okay, the next question. What is the usual amount of data collected during driving for one day?
During one day, I haven't.
Maybe you have another well, timing for an example.
So if you want to do so, some of the tests must be done with a stationary car. You have to show a driver all the functionalities. Very often, especially in Germany, people are not familiar with automatic cars. So first you need, let's say, 15 minutes to drive a little bit with the car to make the participants familiar with it. You need a further, let's say, half an hour to talk about the legal stuff. I told you that we need special agreements from every driver to be allowed to use the images of the face. And then usually a complete data collection takes 1 hour. So if we have 1 hour of data, we need about 2 hours if we have night drives and drowsy drivers and bring them back home after the test drive. This can take much more. So with this, usually we have 2, maybe 3 test drives a day in one car, and then of course it depends on the number of cars you have. If you're interested in the amount of data, you can think of a 2 megapixel camera with usually 2-bit, 12-bit, so 1 byte per pixel, so 2 megabytes data per frame. Then you have a frame rate of 50 to 60 frames per second, and the rest is only mathematics to multiply with seconds, minutes, and hours. You can do it yourself. I don't have the exact number, but we talk about terabytes of data when we talk about a complete test campaign with 500 participants.
Okay, next interesting questions. You mentioned systems should be connected to the car wiring, like CAN or Ethernet. What about the legal part of using this system on public roads in Europe? As far as I know, not I, but the person who asks, it's illegal to use any modified cars in Europe.
No, of course it's not. By the way, when I talked about Ethernet, I'm talking about automotive Ethernet. You were referring to this slide, CAN and Ethernet. CAN is quite easy because you can listen to a CAN without making any changes of the signal. This is also possible in our own cars. For Ethernet, we very often need the help of the OEM, who has special allowances in Europe, but also in the US and in Asia, to drive around with these cars, and then we receive a document that the changes of the car are not relevant for any functionality of any assistance system. I mean, the question is very, very good. You cannot make changes in the CAN and then emergency brake takes place because you have made an error. This must be avoided. And here we very often need the help of the OEMs.
Okay, next question about safety. When would the driver be warned about a scenario that an autonomous car cannot handle? If the time frame is very short, well, probably it should be short. Yeah, so what is the time here?
Yeah. This is I think that the numbers are still varying a little bit. the first thing you need to know, if you have a level 3 vehicle, this vehicle must guarantee that the next couple of seconds it is still able to handle the situation. This time very often is assumed to be about 10 seconds. So if the car the car must be able to recognize situations that are 10 seconds in the future, and then the driver has to be informed to take over the responsibility. And with this, you also have the same 10 seconds to check that the driver is still awake. So it's not necessary to tell the driver to observe the street in the same way that he is doing when he's driving manually. So if you are looking to the side for, let's say, 10 seconds, this is completely okay. But you have to guarantee that the driver does not fall asleep or is so distracted that he is no longer aware that he is responsible for the car. And what is usually done is the eyes of the driver are observed. If the eyes are not visible for security reasons, it is assumed that the eyes are closed. And if the eyes are closed too often, or if microsleep is detected, or if the driver is no longer reacting, then you can do similar things you do with the drivers of trains, namely the security device. You can ask the driver to press a button and ask him, "Hey driver, are you still able to take over responsibility?" And if then the driver says, "Yes, I am," then you can go on with autonomous mode without any further influence to the system. So usually you have two levels. You have the direct driver observation with the camera. And if the camera has any problems in detecting the driver, then you also have a second level asking the driver, "Hey, are you still there?" And if he says, "Yes, I am," then you can trust him and go on with level 2 driving.
Another question, is machine learning or artificial intelligence used in similar systems? Well, if yes, what functional areas do they cover?
Yes, it is used for especially the image processing software to detect the driver's eyes, to find landmarks and so on. In the meantime, use also artificial intelligence, neural networks, especially algorithms that try to detect facial expressions for emotions do not work without artificial intelligence methods, because there is no deterministic idea how muscles in your face must move that you look happy, angry, sad, or whatever. So in this area, AI is used. Yes.
Okay, next one. How does the GT device's performance regarding head or eye recognition with LiDAR camera mapping?
Sorry, I didn't get the question completely. Is it in?
Yeah, it's in Q&As. I believe the question is about how all this data mapping with each other, like this head and eye recognition device and LiDAR data, how it's mapping with each other.
How is it?
It's Gian Pineda, I believe, or sorry if I
Gian
pronounced it
Pineda,
wrongly. Yeah.
544. Regards HGT, would NCAP agree to transfer the responsibility to the driver to wear a vehicle device to meet the regulation of driver monitoring?
I believe this is another question from
Okay,
this person,
sorry.
but still, Still, let's answer this one. Okay, let's proceed with this one.
How does the GT device performance regarding head-eye recognition with LiDAR camera mapping? Well, LiDAR usually is not used for observing the interior of the car. So if you here think of a LiDAR, a radar, or a camera observing the environment, and this tells you a position outside the car where something interesting for the driver is happening, then you can imagine that it would be interesting to check whether the driver is really observing this part of the environment, to know whether he is aware of this situation that might change in a relevant way. But if you consider that let's say if 20 meters in front of you, a person is standing at the side of the lane, and you want to know whether he makes the first step on the street or whether he is still standing there, then the 2 degrees area is a very big area. So this is interesting. There's also a lot of IP known in the last couple of years, but it's still not that easy. But of course, if the driver the driver's gaze is observing the infotainment screen for a long time, and something really interesting happens outside, then of course a synchronization of the systems that are observing the environment and the system that is observing the driver are reasonable. But this is not on image processing level. This is more on a higher level, and for this you do not need this big amount of ground truth systems to look for the raw signals. Hope this more or less goes into the direction of the question.
I believe we have not so much time to cover all questions, because we have 12. So I believe if we have like 5-7 minutes more, could you please pick up like the most interesting from your perspective, like 2 or 3 questions more from the list? And why you are reading and choosing, I would like to tell you guys that we'll definitely send the recorded version of all webinars to you, but it will be next week because we'll upload all sessions at the same time. We'll upload on our YouTube channel, so you'll be able to review it again. And of course, we'll send the PDF of the presentation. So again, you'll be able to check it one more time and review the files.
Mm-hmm.
So did you choose?
Yeah, maybe the question from Juan Pineda again, with the ADAS level 3, what would be the redundant system to warranty the driver attention? As I said, for level 3, the most important thing you have to guarantee is that the driver is still able to take over responsibility after about 5 to 10 seconds. So you have to guarantee that the driver is not sleeping. The highest level is to use the driver camera to see whether the driver is moving his head in a reasonable way. So if he is doing intended head movements, or whether the eyes are open, or whether the blink rate of the eyes are in a reasonable area. This is the first level. The second level would be at any time when the driver is using any keys of the inside the car. If he is starting a phone call, if you can recognize that that he is just talking to another person by telephone, whether he is changing the seat position or whatever he is doing inside the car, this can be recognized by the car on a second level. The idea is the driver who is doing something is not sleeping. And if all this does not work, let's say the driver is wearing sunglasses that are completely intransparent in IR light, so you cannot see the eyes. The driver is not writing emails or working or whatever. He is only observing the environment and sitting there like this without any movements. Then you can say, okay, it takes at least 10 minutes to fall asleep. And then you can do the same that is done by drivers of trains. You can ask the driver in periods of, let's say, 10 minutes, hey, are you still awake? Then he confirms by pressing a button, and then you can leave him alone for the next 10 minutes. And whether 10 minutes are reasonable or not must be discussed by the OEMs. But these are the three levels you can use for driver observation for level 3 driving. Okay.
It's hard to choose, right?
Yeah, the last question is again is a question: what do we do if we know the driver's face, the driver ID? Of course, it's possible to register similar to your smartphone, and if the driver is recognized by a driver camera system, then the car can use pre-settings that are special for the driver. And as far as I know, this personalization is already implemented in premium cars from BMW and Mercedes at least.
Okay, cool. Was it the last one, right?
Yeah.
Great. Thank you so much. It was really awesome presentation. Guys, thank you for participating. As I said, we record this session and we'll send all the materials to you as a follow-up soon. Just as soon as I end the webinar, some feedback survey will appear on your screen. So it would be really nice of you if you spend like a couple of minutes filling out this survey, because it will definitely help us to make our online events better and more interesting and more convenient to you. So I believe this is all from our side for today. Wolfgang, thank you for the talk. It was really great. And guys, I wish you really good, well, evening or day or maybe morning for for somebody, and hope to see you tomorrow, because tomorrow we'll have another session about connected mobility and MCVP topic. This is really, well, modern and I believe unusual topic. So hope to see you tomorrow, same time. Okay.
Yeah, I also would like to thank everybody for your interest. Thanks, Julia, for having me in this marathon. It was really a pleasure to talk about this topic. And if anybody is interested in more details, please feel free to contact me. I think Julia will share the presentations, and you can also share my my email address if you want.
Okay,
So
cool.
feel free to contact me.
Cool. Great. Thank you so much. So thank you everybody for participation and see you tomorrow. Bye bye.
Thank you. Bye bye.
Bye bye.